Good evening, ma'am. Am I audible?
Good evening, sir. Yes, sir, you are audible, sir.
Okay, ma'am. Thank you so much.
Good evening, sir.
Good evening.
Sir, you can start, sir.
Okay. Good evening, students. So, last class we were discussing the concept of magnetic flux. Of course, we just started with the lesson electromagnetic induction, and in that lesson, actually, we started with the concept of magnetic flux linked with the surface. Now, we will be discussing the concept of magnetic flux linked with a coil. So here you have some important concepts which you need to understand in order to solve the numerical problems. So those concepts now we shall discuss. The first thing is magnetic flux linked with a coil. Okay, magnetic flux linked with a coil. So this concept we shall discuss now. Earlier we discussed the magnetic flux linked with a surface. So let us consider that we are having a coil like this, so in oval shape. So here you can see this is the coil, and you are having a magnetic field along this direction. Let me represent the magnetic field with a different color. So this is the magnetic field represented by the letter capital letter B, and the area vector can be represented like this. For this coil, this is the area vector. So this is area vector, and this is the magnetic field B. This is the area vector of this coil. Okay. Of course, in two dimension, the coil looks like this. In two dimension, the coil actually looks like this. So here, if I want to calculate the magnetic flux associated with this plain coil having area A, and if it is having n number of turns, then what is the equation for that magnetic flux? Okay. So the equation for magnetic flux, I think we discussed in our last class. So I'm going to apply that. Phi equal to n into B dot A, where n is the number of turns. Okay, n is the number of turns in the coil, and of course B is the magnetic field and A is the area vector. And here you are having this dot product. So when you replace this, you will be getting phi equal to NBA cos theta. Okay, NBA cos theta. Theta is nothing but the angle. Theta is nothing but the angle between vector B and area vector A. Okay, so phi equal to NBA cos theta. So here you can see this is the coil, and the magnetic field is passing perpendicularly. Okay, the magnetic field is passing perpendicularly. So that means the number of magnetic field lines passing through the coil at this orientation, it will be maximum. The number of field lines is maximum in this orientation, because here you can see when the coil is oriented like this, okay, maximum number of field lines can pass through it. So here this means the magnetic field is normal to the surface. That means it is parallel to the area vector. So here magnetic field B is parallel to area vector. So that means theta equal to 0 degree. So in this case, the magnetic flux value is maximum. So 5 max is equal to, when you substitute cos 0 degree, that will give you NBA. Okay. So this is the maximum value of flux when you have the magnetic field parallel to this area vector. So the next case is the same diagram you can consider. Okay, the same diagram you can consider, but the magnetic field is actually perpendicular to the area vector. So like that you can consider now. So let me draw that diagram here. You have that coil like this. You have the magnetic field vector like this. Okay. The magnetic field, when it is like this, the area vector will be like this. So in this case, the angle between the magnetic field and the area vector is 90 degree. So number of magnetic field lines crossing the coil now will be 0, because here you can see magnetic field is like this, the surface is like this. Okay, the area vector is like this. So that means theta equal to 90 degree. Then the magnetic field through this coil will be minimum or it is 0. Okay, phi minimum equal to NBA cos 90 degree. So that will make phi minimum equal to 0. Okay. So this means the magnetic field is parallel to the surface. So that means it is perpendicular to the area vector. Okay. What is the meaning of this? Let me write here. Here, when the flux is minimum, that means the magnetic field is perpendicular to area vector. In other words, it is parallel to the surface. Okay, in both ways you can mention that. Okay, but here you can see when the flux is maximum, that means B is parallel to A vector or perpendicular to surface. So you should understand the terms used here. B is parallel to A, that means it is perpendicular to surface. In that case, the flux will be maximum, that is NBA. Okay. But here B is perpendicular to area vector, that means it is parallel to surface. Okay. So you have to understand how they are actually using the words. Okay. So when they are using words like this, you need to have a good command over the basic concepts. Then only you will be able to give the correct answer to the question. So here they may be using these words interchangeably. Okay. They may mention that the magnetic field is parallel to the surface in one problem. In another problem, they may mention the same situation but by using different words, like the magnetic field is perpendicular to area vector. Okay, both are the same scenario, but they may use the different words. B is perpendicular to A or B is parallel to surface. Here it is B is parallel to A and B is perpendicular to surface. Both mean the same thing, but they may use different words. Okay, so in that case, you need to very careful while answering the questions. Right. So now we have understood what is meant by magnetic flux. Okay, we have understood what is meant by magnetic flux. Now we are moving on to the concept of electromagnetic induction. Electromagnetic induction. Okay. So before I am going to explain you what is meant by electromagnetic induction, can you tell me what do you know about this electromagnetic induction? Do you know anything about this electromagnetic induction? Whatever you know, you can unmute yourself and you can talk. Okay. Whatever you know about this electromagnetic induction, you can unmute yourself and you can tell here.
Sir,
Yes, please tell me.
so the process of generating electric current by using the magnetic field, sir.
By using the magnetic field, or to be more precise, by
varying it,
changing, yes, by changing the value of magnetic field. Okay, you should actually change the magnetic field linked with the coil. To be more precise, you need to change the magnetic flux linked with the coil. So in that process, what you can do, you can induce some current, okay, by creating some EMF, that is called induced EMF. Induced EMF is generated whenever you create a change in magnetic flux linked with the coil. So initially it was Faraday. Okay, it was Faraday, the scientist who proved this concept of electromagnetic induction. Okay, Michael Faraday. How did he prove that? So for that, let me draw a diagram. Okay. So here there is a coil like this, and this coil is connected by a wire. So this coil is connected by a wire like this, and you have a galvanometer connected here. Now there is a bar magnet here. Okay, there is a bar magnet here. The bar magnet is having north pole here, south pole here. Okay. So now my question is, here we are considering the scenario. The magnet is actually held stationary. Okay, the magnet is now held stationary. Magnet is held stationary. That means velocity of the magnet is 0, and initially Faraday found that when you bring a bar magnet closer to the coil, but you are not at all moving the bar magnet. Okay, you are not at all moving the bar magnet. Just you are bringing the bar magnet near to the coil, and now the bar magnet is kept stationary. Okay, here you have a galvanometer. So he finds that the galvanometer does not show any deflection. Okay, the galvanometer does not show any deflection here. The galvanometer does not show any deflection when the magnet is held stationary. Okay, then what he is doing? Okay, he is actually bringing the north pole of the magnet nearer to the coil. Okay, bringing the north pole of the coil nearer to the north pole of the magnet nearer to the coil, and it is moving with velocity v towards the coil. Now Faraday finds that the galvanometer is showing some deflection. Okay, and that deflection is in this direction. Okay, so that deflection is in this direction. When the north pole of the magnet is moved with velocity v closer to the coil, the galvanometer shows deflection right like this. That is, the galvanometer is deflected to the right, towards the right. Okay, when the north pole of the magnet is brought closer to the coil with velocity v, the galvanometer shows deflection like this. Now the second scenario. Okay, now let us consider the second scenario. In the second scenario, actually what he is doing is, the bar magnet is moved away from the coil like this with velocity v. Okay, it is in opposite direction to the earlier case. In earlier case, the bar magnet is brought towards the coil with velocity v. In that case, the galvanometer shows deflection towards the right. But now, actually, the bar magnet is moving in exactly the opposite direction with velocity v. Now, what is the deflection in the galvanometer? Okay, the deflection is now exactly in the opposite direction. Okay, like this. So, what is your inference from this experiment? Can anyone tell me? I have explained you 3 scenarios. The first thing is the magnet is held stationary. There is no deflection in the galvanometer. In the second case, I have brought the bar magnet with velocity v with the north pole facing the coil. The bar magnet is moved towards the coil. The galvanometer shows deflection on the right hand side. And when you move away the bar magnet with velocity v from the coil, then the deflection of the galvanometer is in the other direction. Now, what is your inference, or what is the explanation for this phenomena? Can anyone tell me? What is happening actually there when the bar magnet is moved towards or away from the coil? You can unmute yourself and you can talk, no issues. Yes, students? Okay, someone has mentioned in chat box. Why can't you unmute yourself and talk? Dana Lakshmi, I think.
Sir,
Yes.
sir, the change in magnetic field induces the current, sir, and this shows the deflection in galvanometers.
Absolutely correct. Okay, your explanation is correct. So, when the bar magnet is moved towards the coil, there is a change in magnetic flux in one direction, and due to that, EMF is induced in the coil, and due to the EMF, current is produced in the circuit. That current is detected by the galvanometer. On the other hand, when the bar magnet is moved in the opposite direction, in that case, the change in magnetic flux is in the other direction. So, the induced EMF will lead to the creation of induced current that will flow in the opposite direction in the circuit. And due to that, the galvanometer deflection is also in the opposite direction. Okay, right. So then the next scenario I will explain now. Okay. So the bar magnet is now moved with the south pole facing the coil. Okay, initially it was north pole, now it is south pole. It is moving with velocity v towards the coil. Okay, when the north pole was moved towards the coil, okay, the deflection of the galvanometer was in this direction. Okay, when the north pole was moved. Now the south pole of the magnet is moved towards the coil. Now, in what direction the galvanometer deflection is? Is it in the same direction as it was in the case when the north pole of the magnet is moved towards the coil? Will it be in the same direction, the galvanometer deflection?
No,
What?
sir. In the
No, sir.
opposite direction.
No, sir. Opposite direction.
Yes, it will be in the opposite direction. Okay, because now the south pole is moved towards the coil. Okay, that means the induced current flows in the other direction. So that is detected by the galvanometer as shown by deflection in the galvanometer in this direction. And when you move the south pole away from the bar magnet, okay, away from the coil actually, when you move the south pole away from the coil, then the deflection will be in the opposite direction. Okay, for the same scenario, south pole of the bar magnet, when it is moved with velocity v, but if it is in the other direction now, that is, it is moved away, south pole is moved away from the coil. So in that case, what will happen? The deflection will be in this direction now. Okay, so that means the direction of induced current flow is also important, and that changes according to the situation. Okay, in which direction you are actually moving the bar magnet towards or away from the coil, and also which pole of the magnet is actually moved towards or away from the coil. All these things are important. That decides the direction of induced current flow. So everything is important. Okay. So now my next question is, if you keep the bar magnet fixed and if you move the coil towards or away from the bar magnet, will there be any induced current flow in the circuit? This is my next question. Please observe carefully. Bar magnet is kept fixed. Now the coil is actually moved towards or away from the bar magnet. Will there be any deflection in the galvanometer? Bar magnet is fixed and the coil is moved towards or away from the bar magnet. Now will there be any deflection in the galvanometer?
No, sir.
Yes, yes. Please repeat.
The deflection will be found, sir.
Yes, deflection will be there because what matters here is only the relative motion between the magnet and the coil. Okay. So when there is a relative motion between the magnet and the coil, you will get induced EMF and then induced current. So even though if the bar magnet is kept fixed and the coil is moved, okay, you will be getting EMF and induced current also. So from these experiments, Faraday concluded that whenever there is a change in magnetic flux linked with the coil, EMF is induced. Due to the induced EMF, induced current also flows. Okay. Okay. Now we have the next scenario. Okay. And one more thing I want to ask you. When the velocity of movement of the bar magnet, okay, when it is increased or decreased, Will it affect the induced current value in the circuit? This is my next question for you. When the velocity of motion of the bar magnet, or in the case when the bar magnet is fixed and the coil is moved, okay, will the velocity of motion of the bar magnet or the coil, will it affect the value of induced current in the circuit? Yes, students, you can unmute yourself and you can talk.
Yes, sir.
Yes, you please tell me, will there be any effect on the value of induced current in the circuit when the velocity of motion of the magnet or even the coil changes?
So the deflection will be large, sir.
Yes, absolutely right. When the velocity of the relative motion is more, okay, the deflection of the galvanometer is more. What does it mean? What is the meaning of that? And why it is more, the deflection?
So if the bar magnet is moved faster, the deflection will be large, sir.
Yes, the reflection is large. Your answer is absolutely right. I am asking, what is the reason for the large deflection in galvanometer?
So the current flow is
Induced current is large. Okay, the
yes,
induced current is large. The value of the induced current is more. So, due to that, the deflection in the galvanometer is also more. Okay, right. So then the next thing is we can have this kind of setup. Okay, I will write that in the next page. Okay, if we can have this kind of setup. So let me draw that here. So here you are having a battery. This is the battery. This is the negative terminal of the battery. Okay. And to this battery, you have a coil connected here, and there is a rheostat here. Okay. So here you have a rheostat, and this battery negative terminal is connected to a coil. Okay. So this coil is called primary coil, and of course you may attach a key here. Okay, to switch on or off the circuit. And I have a second part of the circuit here. Second part of the circuit is here like this. This is a galvanometer. So this coil is called the secondary coil. Okay. We have a galvanometer here. represented by this symbol. Now, I am asking you a question. I am actually connecting this battery with this primary coil. Of course, you may have a switch here. Okay. So, switch, or it is called key. Okay. It's otherwise called a key. So, like this, like this. This is the connecting point, and we have the key like this. So this is the key, and this is the battery. This is the rheostat. This is the secondary coil, and this is the galvanometer. And now I am asking you, when the battery is connected to the primary coil, okay, current starts flowing through the primary coil. Okay, will there be any deflection in the galvanometer here that is connected to the secondary coil? Will there be any deflection? Here, the battery is connected to the primary coil. You have a secondary coil here. Now I am connecting the battery to the primary coil. That means current starts flowing through the primary coil. And you have a secondary coil here connected with a galvanometer. Will there be any deflection in the galvanometer when the primary coil carries some current due to the presence of this battery? Can you tell me? Yes, students, you can unmute yourself and talk. Even though if it is wrong, then no issues. Okay, we are here to learn only, so you can give it a try. No issues. Okay, please don't feel shy to give your answer. You can just tell whatever you know about this scenario. When the battery is connected, current flows through the primary coil. Due to that, will there be any deflection in the galvanometer connected with the secondary coil? You can unmute yourself and talk. Yes, students. Nobody is replying. What happened? Are you feeling shy to give the answer, or do you have any hesitation? Okay. So here the battery is connected to the primary coil. That means current flows through the primary coil. So due to the current flowing through the primary coil, there will be a magnetic field around the primary coil. Okay. So at the moment the battery is connected to the primary coil, current starts increasing in the primary coil for a fraction of seconds. Okay, because it is a DC, the current value remains the same. Okay, once the battery is connected, at that point of time for a fraction of seconds, the current through the primary coil increases from 0 to the maximum value, and at that point, okay, there will be a magnetic field generated around the primary coil, because we all know very well, if a coil carries current, there will be magnetic field around it. So due to the presence of battery, okay, the current through the primary coil increases for a fraction of second, and due to that there is a changing magnetic field around the primary coil. Since the secondary coil is located close to the primary coil, the change in magnetic flux around the primary coil is also linked with the secondary coil. So secondary coil also experiences some change in magnetic flux, okay, due to the change in current in the primary coil. So due to the change in flux in the secondary coil, there will be an EMF induced, and due to that there is an induced current in this circuit of secondary coil, and due to that the galvanometer will show some deflection, okay. But that's just a momentary deflection. Why it is momentary deflection? It is DC, okay. The battery here supplies DC. DC means direct current. The value remains the same. So once you switch on the battery, or once you connect the key here, current increases from 0 to maximum for a fraction of seconds, and in that period there will be a changing magnetic field around primary, and due to that there will be a changing magnetic flux in the secondary coil. So what happens is there is a momentary change in magnetic flux. Due to that there is a momentary induced current flowing through the circuit. So there is a momentary deflection in the galvanometer, okay. That is momentary. Why it is momentary I have explained you. So now what you can do is you can vary the current with the help of this rheostat. Vary the current flowing through the primary with the help of this rheostat. If you increase the current flowing through the primary with the help of this rheostat, okay, there is an increase of current through the primary. Due to that there is an increase of magnetic flux with the secondary coil, and due to that there is an increase of induced current in the secondary coil, which can be identified from the galvanometer deflection, okay. So what happens here is the secondary coil, even though it is not connected with any source of electricity, it is actually getting induced current, okay, due to the presence of this primary coil, okay. So this is also another experiment in which Faraday found that EMF can be induced in neighboring coil also, okay, by changing the magnetic flux in the primary coil. This is one more experiment to prove the concept of electromagnetic induction, okay. So now, based on these concepts, Faraday has given two laws. The first law is, we know very well, okay, the first law we know very well. Change in magnetic flux leads to induced EMF, okay. Leads to induced EMF. This is the first law, and you have the second law as well. So what is second law? It gives you the value of the EMF, okay. Gives you the value of the EMF. So that EMF is represented by the letter small letter E. E equal to minus d phi by dt. D phi by dt means change in magnetic flux. That is the rate of change of magnetic flux. So EMF produced is equal to minus d phi by dt. That means the EMF induced always flows in a direction, okay, to oppose the change in flux, okay, to oppose the change in flux. So this can be explained by Lenz's law, okay. This can be explained by Lenz's law. Why there is a negative sign here? This can be explained by Lenz's law. But the one thing you need to understand is the EMF equal to minus d phi by dt. When there are n number of turns, okay, when there are n number of turns in the coil, then your EMF is E equal to minus n into d phi by dt, okay, d phi by dt. So this is the second law. So now we shall see how Lenz's law explains this negative sign, okay. Actually, when you bring the bar magnet closer to the coil in earlier cases, okay. So here you see when the bar magnet, okay, is moved away from the coil. That means the south pole of the magnet is moved away from the coil. What happens is the induced current flows in this coil, okay. Here the south pole of the bar magnet is moved away from the coil. Due to that, the induced current flows in the coil in such a way that this end of the coil becomes a south pole, becomes a north pole actually. I think you can understand this because here, let me explain again. So here you see when the south pole of the magnet, okay, when the south pole of the magnet is moved away from the coil, what happens is the induced current flows through the coil in such a way that, okay, due to the induced current, there is a magnetic field produced by this coil also, okay, because here induced current flows in this coil means that will also generate some magnetic field around it. That means it generates magnetic field around it means it itself becomes a bar magnet. So when the south pole of the magnet is moved away from the coil, induced current flows in coil in such a way that this end, okay, this end becomes a north pole, so that it opposes the movement of this bar magnet away from it. Okay, I think you can understand when this bar magnet is moved away from the coil, induced current flows in the coil in such a way that this end, okay, this end becomes a north pole, so that it opposes the moving away of the south pole from this coil. Okay, so it means here EMF is produced only due to the movement of south pole away from the coil. So that means the cause, okay, the cause of EMF here, the cause of EMF here is movement of south pole away, okay, movement of south pole of the magnet away from the coil, away from coil. Okay, this is the cause of EMF. And how the induced EMF flows in this coil, in which direction the induced EMF flows in this coil. So the induced EMF flows in this coil in such a way that, okay, the nearer end, okay, so here you see the nearer end here becomes north pole, okay, the nearer end becomes north pole. Usually there is a force of attraction between the north pole and south pole. So when you try to move the south pole of the bar magnet away from the coil, this end becomes north pole such that it opposes the movement of south pole away. That means here induced EMF flows in such a way, okay, induced EMF flows in such a way that, or such a direction that it opposes, okay, in such a direction that it opposes the cause of production of the EMF, opposes the cause of production of the EMF. That means in this case the south pole of the bar magnet is moved away. This is the cause for the EMF production. So due to this, the nearer end becomes north pole, so that it opposes the movement of south pole away from the coil. So if you think about the other scenario, that is when you bring the south pole towards this coil, in that case what happens? Okay, when you bring the south pole towards this coil, in that case what happens? We shall consider that also. So when you bring the south pole towards the coil. South pole towards the coil. Here, cause of EMF is the movement of south pole of the magnet towards the coil. Okay, here the cause is movement of south pole of the magnet towards the coil. Towards the coil. So here south pole is moved towards the coil. This is the cause. Then induced current flows through the coil in such a way that the nearer end becomes south pole. Okay, the nearer end becomes south pole. So when this end becomes south pole, what will happen? The bar magnet is having south pole here. When the south pole is brought towards the coil, this is the cause of EMF generated now. So the EMF flows in the coil in such a way that this end becomes south pole, so that it repels the south pole from coming towards it. Okay. So it leads to repulsion. That means it opposes the cause of production of EMF. Cause of production means the bar magnet is now moved towards the coil. That is the cause. So the EMF induced in the coil actually flows in such a way that it opposes the cause. Opposes the cause means cause is here, movement of the south pole towards the coil. So it opposes the cause. So if it has to oppose the cause, then this end becomes the south pole. Okay. Now, students, do you all understand this concept?
Yes, sir.
Any difficulty you have in understanding this?
No, sir.
Okay, fine. So this is called Lenz's law. In this way, Lenz, the scientist, explained why there is a negative sign here. Okay, negative sign means the EMF flows in one direction, the rate of change of magnetic flux is in opposite direction. Okay, that is the meaning of this Lenz law. In this way, Lenz has explained everything. Okay. Right. So this is the meaning of Lenz law, and this is how Lenz explained everything. Now, I have one question for you. Now I have one question for you. Lenz law is the consequence of the law of conservation of option A, charge, option B, momentum, option C, mass, option D, energy. This is my question. Can anyone answer this?
Sir,
Yes, please.
energy.
Yes, you are absolutely right. It is energy. Okay. Lenz law is the consequence of conservation of energy. And why it is energy? Because if the induced current flows in such a way to support, okay, the induced current flows in such a way to support the cause, okay, then what will happen? Once the induced current starts flowing, then there will be no decrease in value of induced current. Only there will be increase in value of induced current without us putting any effort. Okay, without us putting any effort. That means you just bring the bar magnet towards the coil, then EMF starts flowing through the coil for an infinite amount of time. Okay, because if the induced current flows in such a way to support the cause of that EMF production, then once you start creating induced EMF, then the induced EMF and induced current flows through the circuit for infinite amount of time. Okay, just by initiating that process. Okay, that means you don't have to move the bar magnet also, because the induced EMF supports the cause, means the induced current flows in such a way that it supports the cause. That means it itself causes the bar magnet to move towards or away from it, and itself generates induced EMF without us putting any effort. That means you don't give any input of energy there, but you are getting lot of induced current. Okay, that is not possible. That violates conservation of energy. So Lenz's law here, when it opposes the cause of EMF, only then only what you will do, you will continue doing the work. That is, you will try to move the bar magnet towards or away from the coil. That is your work. You are doing some work against the repulsion. Okay, repulsion means, what I am telling here is against the flow direction of that induced current, you actually do some work. That work is converted into EMF. So like that you need to understand. So Lenz's law is the consequence of the law of conservation of energy. Okay. Okay. Now I have my next question. Okay. So please try to answer this. The magnetic flux. Okay. The magnetic flux linked with a coil is given by an equation. Phi. Okay. The unit of phi is Weber. So in Webers, so phi equal to 8t squared plus 3t plus 5. The induced EMF. The induced EMF in the coil. In the coil at the 4th second. At the 4th second will be. This is my question. And I am not giving you the options. Now, can you tell me what is the answer for this question? The magnetic flux linked with the coil I have given you. Now you have to find out the induced EMF in the coil at the 4th second. You please calculate and then tell me what is your answer. Yes, students, have you completed? If you are completed, you can unmute yourself and you can tell me the answer. Yes, students, we have 1 more minute left in the session. Have you all completed this? Has anyone completed this? Very simple question now. So it is E equal to minus d phi by dt. That means you have to differentiate this equation with respect to time. So minus d by dt of 8t squared plus 3t plus 5. When you differentiate this with respect to time, you will be getting 16t plus 3. Okay. So they have asked us to find out the induced EMF at t equal to 4 seconds. So EMF equal to E equal to minus of 16 into 4 plus 3. So that will be minus 67 units. Units means it is volt. Okay. This is your answer. Does anyone have any doubt in it? Students, does anyone have any doubt in the solution for this problem?
No doubt, sir.
Okay. So thanks for joining the session. Let us continue with our discussion on electromagnetic induction in our next class. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.